All right, let me start in a simple way. When people hear about modern physics, they often imagine something distant, abstract, and cold equations flying around like mosquitoes on a summer night. But physics is not really about equations. Equations are just the language we use after we already understand something. Physics is about noticing how the world behaves and asking again and again why it behaves that way. So, let me begin with a question that sounds childish but is actually very deep. Why do things have weight? Or, if you prefer a more careful word, why do things have mass? Why is it hard to push a refrigerator but easy to push a pencil? Why does light move so easily while you and I do not? At first glance, the answer seems obvious. The refrigerator is heavy, the pencil is light, but that is not an explanation. That is just a restatement of the problem using different words. Physics is not satisfied with that. It wants to know what is going on underneath. For a long time, people thought mass was just a basic property. An object simply had it the way it has a color or a shape. End of story. But the deeper we looked, the more uncomfortable that answer became, especially when we started to understand nature at its smallest scales. The world stopped looking like solid stuff and started looking like activity, little points, exchanges, and movements. In that picture, mass becomes a problem, not a given. If we zoom in far enough, we find that what we thought was a thing is actually an interaction. To understand this, we have to accept a reality that breaks our intuition. Empty space is not empty. If you take all the air out of a box, and then all the atoms, and then all the radiation, you do not get nothing. You get a very busy place. Space itself has properties. It can stretch, vibrate, and store energy. And the NG in modern physics, space is filled with things we call a field. A field is not a thing you can hold. It is more like a condition. Think of temperature in a room or wind in the sky. You do not ask where the wind particle is. You ask what the wind is doing here. In the same way, nature is described by fields that exist everywhere, even where there are no particles. Once you accept that the world is made of fields, you start to see that particles are not solid beads, but small localized vibrations of those fields, like ripples on the surface of a lake. This perspective changes everything. It means the emptiness between stars is actually a medium with its own specific geography. To map this, we use the language of calculus, not to solve boring textbook problems, but to describe how a field changes as you move through it. We are essentially looking at an energy landscape where nature is always trying to find the easiest path. Light gives us a beautiful clue here. Light has energy and momentum, yet it has no mass. It races along at the absolute speed limit of the universe because it doesn't experience any drag from the vacuum. Electrons, on the other hand, do have mass. They respond sluggishly when you push them. Both are vibrations of fields spread throughout space. So why does one behave as if it is heavy while the other acts weightless? This question haunted physicists throughout the 20th century when they looked at the equations that describe the fundamental forces of nature. They found a startling problem. The math only worked perfectly if everything was massless. The equations possessed a beautiful symmetry, a balance that allowed the laws of physics to look the same no matter where or when you performed an experiment. However, as soon as physicists tried to add mass into the equations by hand to match the reality of refrigerators and pencils, that symmetry shattered and the math became a mess of inconsistencies. Nature, clearly, did not agree with equations that only allowed for massless particles. After all, we exist, and tables exist. This created a profound tension. How could the fundamental laws of the universe demand weightlessness, while the physical world was so obviously heavy? The resolution required us to rethink the very nature of the vacuum and how a field settles into its settled state. To solve this, we have to look at how nature makes choices. We often think of symmetry as a purely aesthetic quality, but in physics, it is a strict constraint on what is possible. Imagine a pencil balanced perfectly on its tip. That situation is symmetric in every direction. There is no reason for it to fall one way rather than another. Yet, the pencil cannot stay that way. The slightest disturbance makes it fall, and when it falls, it chooses a specific direction. The laws of physics that governed the pencil were symmetric, but the outcome was not. This is called symmetry breaking, and it is the secret to how the universe gained its substance. Just like that pencil, certain fields in our universe do not stay in a state of perfect, weightless balance. Instead, they roll down into a valley of the energy landscape. Nature prefers low energy, much like a ball prefers the bottom of a hill. The point where the field finally stops and stabilizes is what we call its settled state, or the vacuum. But here's the catch. Because of the way this specific field is shaped, its settled state is not zero. Most fields, like the electric field, settle at zero in empty space. If there's no charge, there's no field. But this field is different. Even in the deepest, emptiest void, it maintains a non-zero value. Space itself is soaked in it, like air filling a room or the ambient temperature of a house that never drops to absolute zero. This brings us to the core thesis of how weight actually happens. Once this field settles into its non-zero background state, it creates a structured vacuum that everything must pass through. If you are a particle moving through this space, you are no longer moving through a void. You are moving through a medium. Some particles pass through this background easily, barely noticing it. Others, however, experience a constant, clinging interaction. This struggle against the background is what we perceive as inertia. It is why it is hard to push a refrigerator. The refrigerator isn't heavy because of some internal stuff it contains. It is heavy because the particles making it up are constantly being slowed down by their interaction with the field that is already there. This shift in perspective completely dismantles the old coins in a pocket misconception. We used to think mass was something a particle carried around inside itself, but we now see it is an emergent property. It is a relationship. A favorite way to picture this is to imagine a crowded room filled with people standing around. If a person nobody recognizes tries to walk across the room, they can move in a straight line without much trouble. They don't interact with the crowd, so they move quickly. But if a famous person enters, people cluster around them. They slow that person down, making it harder for them to change direction or speed up. From a distance, it looks as if the famous person has acquired a huge amount of mass. Yet, nothing has been added to the person. The difference comes entirely from the interaction with the environment. In the subatomic world, mass arises exactly the same way. The equations of physics can remain perfectly symmetric and elegant because, fundamentally, the particles themselves are still massless. The weight we measure is just the drag created by the field in its settled state. This is why the energy landscape of the vacuum is so important. If that landscape were shaped differently, if the valley where the field sits were shallower or deeper, the weight of everything in the universe would change. Atoms might become too heavy to hold together, or so light they would fly apart. Our very existence depends on the specific, measured stiffness of this invisible background. By looking at mass this way, we realize that moving a refrigerator is actually an act of communal physics. You aren't just pushing against a piece of kitchen equipment. You are pushing against the resistance of a field that fills every cubic centimeter of the cosmos. Advanced calculus sneaks in here to describe the slope of that resistance, teaching us how systems settle where change stops and where the energy is at its minimum. Nature performs this complex calculation at every point in space simultaneously, without ever writing down a single formula. It simply finds the most stable configuration and stays there, quietly giving substance to the world. But if this field is really everywhere, how do we prove it? How do we find a vibration in a medium we can't even see? If the field is real, then logic and mathematics dictate a specific consequence. It must be able to ripple. Just as the surface of a lake can have waves, even when the water as a whole is sitting still, A field in its settled state can have small disturbances around its base value. In the language of modern physics, these disturbances are what we call particles. This is a universal rule. The electron is a vibration of one field, light is a vibration of another, and the field that gives things mass is no different. Its vibration is a unique particle, one that only appears when you hit the vacuum hard enough to make it wince. The problem is that this field doesn't ripple easily. The energy landscape it sits in is incredibly stiff. To use a physical analogy, imagine trying to create a wave in a pool of water versus a pool of thick, heavy mercury. It takes far more energy to make the mercury move because the field we are discussing is so fundamental and its valley is so steep. The energy required to create a single vibration is enormous. This is why the particle associated with it is so heavy and so incredibly short-lived. It doesn't exist freely in nature like an electron does. It is an expensive excitation that nature only allows under extreme conditions. To see it, we have to drop a metaphorical stone into the vacuum with enough force to overcome the field's resistance. This is why we build massive particle colliders. We aren't just smashing things together for the sake of destruction. We are concentrating a vast amount of energy into a space smaller than an atom. In that tiny point of impact, for a billionth of a second, the energy is high enough to shake the field out of its settled state and create a ripple. We aren't creating the field in these collisions. The field was already there, quietly giving mass to the particles being smashed. We are simply shaking the medium hard enough to confirm that the medium actually exists. This confirmation is vital because physics is conservative. We don't accept an elegant idea like symmetry breaking just because it looks good on a chalkboard. We require nature to cast the final vote. If the field exists, the vibration must be there. If we find the vibration, we know our entire picture of how the universe gains its mass, that it is a result of interaction rather than substance, is fundamentally correct. But detecting a ripple that vanishes almost the instant it is born requires more than just high energy. It requires a new way of looking at evidence. Detecting this vibration is a challenge that pushes the limits of human ingenuity because the particle doesn't live long enough to leave a neat, visible trail in a detector. It is unstable and decays almost immediately into other, lighter particles. What physicists actually observe are the decay products flying off in specific, predictable patterns. This is where the narrative of science shifts from the drama of a single aha moment to the rigorous architecture of evidence. No single collision proves anything. Nature is noisy, and many different processes can produce outcomes that look suspiciously similar to the ripple we are looking for. To be confident, we must look at millions or billions of events and search for a pattern that appears more often than chance allows. This is a task of pure statistics. It is like flipping a coin 1,000,000 times to see if it is perfectly balanced or slightly weighted. If the field is real, we should see a tiny bump in the data, a small excess of events at a specific energy level that cannot be explained by anything else. Calculus and probability are the silent engines here, helping us describe how these outcomes pile up and how a small, significant signal emerges from a sea of background noise. When the evidence finally becomes overwhelming, we don't celebrate the particle as an isolated, holy object. In physics, no particle is sacred. Each one is a clue. We celebrate the discovery because it confirms a larger, much more profound picture, a universe where empty space is not empty, where laws are guided by symmetry, and where the mass of a refrigerator is a consequence of a constant, invisible interaction. It proves that our energy landscape model isn't just a mathematical convenience, but a literal description of the medium we inhabit. This realization forces us to admit something important about how we understand the world. We never observe fields directly. We only ever observe their consequences. We infer the wind from the waving of flags, and we infer the field from the presence of mass and the fleeting appearance of its vibrations. This shift from seeing objects to seeing relationships is the hallmark of modern physics. It tells us that the universe is far more integrated and dynamic than our senses suggest. But as with any discovery, the confirmation of the field doesn't end the story. Instead, it places our ignorance on a much more elevated stage. At this point, it is tempting to think the job is done. The field exists, its vibration has been seen, and the case is closed. But that is not how physics works. Every confirmed idea becomes a tool for asking better questions. Why does this field have the particular strength it has? If it were even slightly different, the interaction that gives mass to electrons might be too weak, and atoms would never form. Chemistry would fail, and stars would burn differently or not at all. Physics does not answer these questions by invoking purpose or design. It simply admits that we do not yet know why the energy landscape is shaped the way it is. This honesty is essential. Good physics is not about claiming final truth. It is about narrowing our ignorance in a controlled way. What we have learned is that mass, which once seemed like a primitive property, is actually a result, a kind of resistance caused by moving through a structured vacuum. This way of thinking changes how you look at the world. When you push a table and feel it push back, you are not just dealing with stuff. You are experiencing the interplay of fields, symmetries, and energy landscapes, all working together in a quiet, consistent way. But we must remember that this field explains only part of the story. Most of the mass of ordinary matter actually comes from the energy stored in the motion of smaller constituents within atoms. Even without this field, protons would still be heavy. It is a crucial piece of the building, but it is not the whole building. Beyond its walls lie unanswered mysteries. Gravity doesn't fit comfortably into this framework, and the dark matter that dominates the universe remains invisible to our fields. Physics is not a neat package tied with a ribbon. It is a sturdy but provisional scaffolding, always subject to revision. So, what should you take away from all this? Not the name of a particle or the details of a detector, but a way of thinking. When you push against the world and feel resistance, remember that this resistance is an outcome of an interaction with the settled state of a field that fills all of space. When you hear that something exists everywhere, do not imagine a substance, but a condition. Confusion is not the enemy of understanding. It is the beginning of it. Nature is subtle, and if you ask clear questions and listen carefully to the answers, it will tell you how it works honestly and with a deep respect for the mystery that remains.